For this problem, we are supposed to sketch f of x is equal to x squared over x squared minus 4. Be sure to label all intercepts, local extrema, points of inflection, and asymptotes. And there's a big hint that's given that the first and second derivatives are given, so we do not need to compute those in this problem. First off, let's do the easy things first. Intercepts. We find the x-intercepts first by solving f of x is equal to 0. And in this case, a fraction is equal to 0 exactly when the numerator is 0. And so I would have x squared is equal to 0 or x is equal to 0. So that is the x-intercept. Now, it's redundant in this case, so I don't need to do this, but I'll do it anyway. To find the y-intercept, we plug in 0. So f of 0 is going to be 0 over 0 minus 4, and that's 0. So that's redundant. I already knew that the point 0, 0 was on the graph. I did that here for the sake of completeness. Okay, so that's intercepts. So that's that. Okay, now let's talk about asymptotes. Okay, so first off, vertical asymptotes. The vertical asymptotes occur, vertical asymptotes. The vertical asymptotes occur where the denominator is equal to 0. So I have vertical asymptotes when x squared minus 4 is equal to 0. And so that's x equals 2 or negative 2. And so those are the two places where I have vertical asymptotes. Horizontal asymptote. We figure out the limit as x approaches infinity of x squared over x squared minus 4. And the standard technique is to multiply top and bottom by the highest power, divide top and bottom by the highest power in the denominator. So the highest power in the denominator is 1 over x squared. So 1 over x squared times x squared. Okay, that's equal to the limit as x approaches infinity of 1 over 1 minus 4 over x squared. 4 over x squared, that goes to 0 as x goes to infinity. So this goes to 1 over 1 minus 0, which is 1. Okay, and the same will apply for the limit, and the same will apply for x goes to negative infinity, the exact same logic. Okay, so on the screen here, let me just start putting in the information that we have, and we'll add to this picture as we go along. Okay. So first off, I have a vertical asymptote at 1. Sorry, I have a horizontal asymptote at 1. So that's 1. I have an x-intercept and a y-intercept at 0. I also have vertical asymptotes at negative 2 and another vertical asymptote at positive 2. Okay, so that's the information that we have so far. The horizontal asymptote determines the behavior as x gets large, both large positive and large negative. And I have vertical asymptotes at negative 2 and positive 2. Right now, I don't quite know the direction in which they blow up. Okay, so we continue. So to continue, let's figure out the places where the function itself are positive and negative. So determine where f is positive and negative. Now, this can be done a couple of ways. One way this can be done is by plugging in numbers. My personal preferred approach um, is to look at the graph, the factorization of the function. So I have x squared minus 4 factors as x minus 2 and x plus 2, and these all combine to give me f of x. The points of interest are going to be 0 for x squared, 2 for x minus 2, and negative 2 for x plus 2. x squared, that's equal to 0 when x is equal to 0, and otherwise it is positive. X minus 2 is equal to 0 when x is equal to 2. It is positive if I plug in something that's bigger than 2, and negative if I plug in something that's less than 2. X plus 2 is 0 when x is negative 2. It is negative if I plug in something less than negative 2, and it is positive if I plug in something that is bigger than negative 2. Okay, so we have positive, negative, negative. That makes positive over here. At negative 2, I have a vertical asymptote. Positive, negative, positive means the function is negative between negative 2 and 0. I then have my x-intercept and y-intercept at the origin. Positive, negative, positive means negative again between 0 and negative 2. I have a vertical asymptote at 2. And then 3 positives means the function is positive to the right of 2. Okay, so that's my sign chart for the graph of f of x. Okay, now let's determine where f prime of x, and f prime of x is negative 8x over x minus 2 squared, x plus 2 squared is positive and negative. And in this problem, the derivative was given to us, so there's no need to calculate it. Okay, same kind of logic. I have negative 8x, x minus 2 squared, x plus 2 squared. And when combining all these, I get the derivative f prime of x. The points of interest, once again, are 0, 2, and negative 2. That's a coincidence for this problem. It doesn't have to work out like that. All right. At negative 8x, that is 0 when x is equal to 0. If I plug in something bigger than 0, negative 8x is negative. And if I plug in something that's less than 0, negative times a negative makes positive. For the other two, if x minus 2 squared is equal to 0 when x is equal to 2. Otherwise, when I square something, I get something that must be positive. X plus 2 squared, that's 0 when x is equal to negative 2. When I square something, if it's not 0, it must be positive. Okay, so combining, we got 3 positives makes positive over here. I have a vertical asymptote again at negative 2. 3 positives makes positive over here. I've got a 0 at 0. This is negative, positive, positive, so that makes negative. I have again the vertical asymptote at 2, and then negative, positive, positive makes negative. Okay, so this is the derivative, so the function must be increasing to the left of negative 2. It is increasing between negative 2 and 0. It is decreasing between 0 and 2, and it is decreasing between 2 and infinity, to the right of 2. So that gives me an indication about whether the function is increasing or decreasing from the derivative. All right, finally, let's take a look at the second derivative. So let's determine where f double prime of x, and f double prime of x was 8 times 3x squared plus 4 over x minus 2 cubed, x plus 2 cubed is positive and negative. Okay, the points of it. So the parts of this are 8 times 3x squared plus 4, x minus 2 to the third, and x plus 2 to the third. Those combine to give me the second derivative. And the points of interest this time are only negative 2 and 2, because this top line is guaranteed always positive. 3x squared is always positive. Add 4, positive. Multiplied by 8, positive. there's nowhere that this top line is equal to 0. All right, x minus 2 cubed, that's equal to 0 at 2. If I plug in something bigger than 2, the result is positive. If I plug in something that is less than 2, a negative number cubed is negative. Likewise, at negative 2, if I plug in something that's bigger than negative 2, the result is positive. If I plug in something that is less than negative 2, a negative number cubed is negative. And so the net result is I've got positive here. I've got my vertical asymptote at negative 2. It's negative here, vertical asymptote at 2, and then positive out here. So the graph will be concave up to the left of negative 2. It is concave down between negative 2 and 2, and it is concave up to the right of 2. Okay, so let's put all that together when looking at the graph. Okay, first, the increasing and decreasing behavior. Well, okay, so to the left of negative 2, the graph is increasing and it's controlled by this vertical asymptote. So the graph is going to go upward like this. It's controlled by the horizontal asymptote as I go large negative. As I get closer and closer to negative 2, the graph will increase and increase positive. Between negative 2 and 0, the graph is increasing until I get to this point. And so this point here must be a local max. And then it decreases to the right of 0. So the graph must go like this somehow. It's not quite parabola shaped. It doesn't cross the vertical asymptote, but it's controlled by these two vertical asymptotes. And then finally, to the right of 2, the graph is decreasing. And so I'm between this vertical asymptote and this horizontal asymptote. And just scanning what I see here, it is concave up over here to the left of negative 2. It is concave down between negative 2 and 2. It is concave up to the right of 2. Also looking at my sign chart of the original function, it is positive to the left of negative 2. It is negative between negative 2 and 2, except for 0. And the graph is positive between 2 and plus infinity. And so that is the graph. So this one has a local max at 0, 0. It has an intercept, of course, at 0, 0, and has no points of inflection. And I have the horizontal asymptote at y equals 1. I have the vertical asymptote x equals 2. And I have the other vertical asymptote x is equal to negative 2. And so that is a sketch of the graph using the information that's given. Before closing the video, I did sign charts for these problems. This can also be done by plugging in points. So for example, if I plugged in f prime of 1, I would get negative 8 times 1 over negative 1 squared times 3 squared. That's negative 8 ninths. And the negative 8 ninths is not important. That means less than 0. And so I would conclude that the derivative, the part that I'm circling here in blue here, the derivative would be negative between 0 and 2, because when I plugged in a number between 0 and 2, I got a negative number. If you prefer plugging in points as opposed to sign charts, there is absolutely nothing wrong with that. I did not do both approaches here in the video for the sake of time, but if you prefer plugging in numbers to figure out the behavior, where it's positive, negative, by all means, you are free to do so.